So this is for chapter 24 homework. Deals with electromagnetism and specifically forces on charges that are moving or forces on current carrying wires. So for P5, we've got wire with 10 amps, one wire with an unknown number of amps, and a point here, 1 centimeter from the top, 2 centimeters from the bottom. And the question was how much current's going through the bottom wire if the if the magnetic field is zero at that point. Well, the Biot-Savart law is mu sub 0 times I over 2 pi times r. And that r is the distance from the wire, and I is the current. Everything else is a constant. So in this case, the only thing that would be different would be the distance from the wires, and therefore the current would have to be different as well. So twice the distance means that you would need twice the current to have the same effect. For 13, this is the magnetic field in a solenoid. So it gave you the number of turns, the length of the solenoid. The constant here is for vacuum permeability, and then the current I is here. So this is not on your formula sheet. It's something which is pretty important to understand, at least, that we've got basically the effect of a solenoid. In this case, it was producing 1 Tesla magnetic field. Is something that depends on how tightly the coils are wrapped, more than the diameter or anything else. Problem 25 should be similar to things that you end up doing in active physics. It's relating a magnetic force to a centripetal force. So the centripetal force formula is mv squared divided by r. In this case, the magnetic force is acting as a centripetal force, and that's mv over qb. So the radius for the electron is 0.113 meters, radius for the proton is 10.4 meters. So for number 33, you've got a 2-gram wire here. It's in a magnetic field. It showed you the direction of the magnetic field. I drew a free body diagram first. That's something that's pretty important in terms of understanding how these forces are balanced. So that's the formula for the magnetic force in a wire. That's the force for gravity. I know this from the mass of the wire. I can figure this out, these things except for the field strength, from the other information in the problem. So the field strength has to be 0.13 Tesla. And the direction of the permanent magnetic field is out of the page to cause an upward force for a leftward moving current. And you could either use the flat hand rule or the curvy hand, right hand rule to figure that out. 44. The top part of the wire here will cause a force in one direction. Any magnetic interaction with the bottom part of the wire will cause a force in the other direction, so those cancel out. So the only length we're interested in is this part of the wire, and that's 10 centimeters long. So if you know the voltage and the resistance, you can find the current. Again, current going through that wire is something we can use this formula to figure out the magnetic field strength. And if we see the direction of the magnetic field here and know the direction of the current, we can predict the direction of the force. 46 we went over extensively in class. The tough thing about this was recognizing it's an electric force is equal to a magnetic force, and then thinking about, well, how the heck do we get the electric force? And essentially here, we know the electric field strength is volts per meter, but that also is the same as newtons per coulomb. So that is something you would need to remember. And so E equals F over Q, so the F equals E times Q. Q cancels out on both sides of that equation. The magnetic field would have to be into the page, or X's, to cause this effect on an electron. For P47, this was similar to a conceptual question. The big idea, again, balance forces. You've got 2 springs acting to the left, and then a magnetic force would be pulling to the right. So 2 times K times delta X plus B times I times L. If you only had 1 spring, the spring would be, and the spring was stretched this much, then either it would have to have twice the spring constant, or something would have to change over here. But in this case, a 2 amp force would equal 2 amp current would equal that magnetic force for the other information given. And notice I'm showing 2 springs acting to the left. That should do it. If you have any questions, Make sure you ask in class. This is a tough topic, so again, I would strongly encourage you to not let these go if you did not do a lot of detailed work on the homework.